6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13. 5 million pounds of thrust, and it has cleared the tower.
Prepare yourself for a world of seriousness. This is
Welcome one, welcome all. Conley here, everybody. It is the Science Nights in the morning. I have Dr. Sean Dran all the way from down under, and I also have Dr. Thomas Shiller here in the house with us. And, well, you know what? What are we going to be talking about today, Thomas? You are a geologist, paleontologist extraordinaire, and we have some mysteries to unravel today.
Yes. We're going to talk about the mantle.
The mantle.
Yeah. So
Earth's mantle.
Yes.
Hollow Earth.
Yeah, there's nothing down there. That's what we've discovered. We've drilled to the mantle, and it's in fact hollow and full of dinosaurs.
Yes. See, I knew it.
Yeah.
I knew it.
No,
Full of live dinosaurs. Live dinosaurs,
yes,
right?
and plesiosaurs. Yeah.
Yeah.
And Godzilla.
And Godzilla.
Yeah. So, all right. Well, we figured it out.
Yep. The end. Good job.
Yeah, we got it. So, now what? So we are going to be talking about the mantle.
Yeah. Yeah. So, the deep Earth, or not even that deep, is always kind of mysterious because we can't physically get to it. Mm-hmm. Up until I think in early May is when the drilling happened. We'd only been able to drill in partially through the Earth's crust. So we know a little bit, or we know quite a bit about the crust, but we know very little about the mantle and especially the core. It's like impossible for us to dig that deep. And it hasn't been without trying. In 61, it was attempted, Project Mohole, to dig to the mantle. And the Soviets tried to dig through the crust, or at least get as deep as they could in a traditional well, and they dug down to around 40,000 feet, which is barely a third of the way through the continental crust. So the mantle is very mysterious. We know it's there. We know how thick it is. We know its volume because of geophysics, looking at it indirectly, and we could talk about that a little bit later. But as far as physically visiting the mantle, physically observing the mantle, we haven't been able to do that until earlier this summer. So kind of a big scientific accomplishment, breakthrough. A team of scientists drilling off the coast of the Azores near the mid-Atlantic ridge managed to, or at least they think they managed to get down to the mantle. They broke through the oceanic crust at its thinnest area and retrieved solid mantle rock, which has never happened before.
That's kind of like going to the moon almost. I mean, you could say that, right? I mean,
we got there. We got to the moon sooner than we got to the mantle. That's how difficult it is to drill through Earth's crust.
Yeah, but I mean that's like a giant leap for mankind, or a giant dig for mankind.
It is, and it's kind of the beginning of us better understanding what's going on down there. And there are a lot of implications, a lot of things that we should learn from those solid mantle rocks that were retrieved. Even some biological things, which we'll talk about. But there's several teams that do this sort of science where they go off on what they call cruises. Not like we think of a cruise where you go and drink a bunch of booze and relax and all of that. But these are scientific vessels that go, and they usually have multiple different goals, multiple tasks, and a team of scientists who specialize in different sort of disciplines. Because when you look at the oceanic crust and the seafloor, you have a lot of different components there, a lot of different scientific interests, right? You have the biological interests, studying what's living on or in the substrate of the seafloor, hydrological interest, the composition, the temperature of the ocean at great depth. And then you have the geological interest of the composition of the sediment that sits on top of the oceanic crust and the solid oceanic crust itself. Wow. So these vessels for years and years, decades, have been going out into the ocean and gathering samples from the seafloor and drilling down into the oceanic crust and retrieving solid rock samples. So a lot of what we know about plate tectonics, the composition of the seafloor, the thickness of the seafloor, what's going on down there is derived from these expeditions. And the reason I'm aware of these is not just because of this news. A buddy of mine from Texas Tech, who I discovered about an hour ago, actually participated in this groundbreaking expedition.
Oh, wow, cool. All right.
Had I known sooner, I would have invited him on the show. Maybe we can have him
For sure.
sometime soon. But he went on these cruises, even as a grad student, as a PhD student. I think he went on 2 or 3 because he was interested in the structural components of the seafloor at the time. And they go out for weeks and they drill. The biologists gather living samples. The hydrologists gather water samples. The geologists bring up core samples from a drill. And it's really a cool operation. Yeah. And it's all done from a boat. So I'm trying to picture what's going on here. There's a boat with a big drill attached to it going down. Yeah. And so they have to drop it, maybe a mile or 2 through the ocean to get to the ocean floor. And then the drill's got to keep on going. And the whole time the ship has got to be still enough that drill bit doesn't shake or break or something like that. Yeah. It's got to be pretty tough. Yeah. And they were doing this in the 60s. Like I said, in 61, and this was a sort of U.S. Sponsored program, the Operation Mohole, which sounds kind of dirty, but we'll talk about what that means, to drill as far down as we could into the oceanic crust. And it failed, but that doesn't mean it wasn't entirely useful. But this one was the most recent one was a success. Got all the way down to the. So Thomas, what's the difference? So it makes sense. Like from a amateur perspective, you go, okay, well, where's the thinnest crust? And I guess it's the oceanic crust, right? Mm-hmm. And where it's spreading, and the mid-ocean ridge. Yep. And then you drill there. That makes total sense. So what went wrong in 61 and what changed now? Like they basically used the same basic setup, the same hypothesis, but this time they struck gold. Yeah, so what changed? The 61 expedition had some logistical issues. The company that was hired to do the drilling was not a drilling company. So that was problematic at the beginning. It was a construction company, Brown and Root, a Texas construction company. Sure. Right. It's like Halliburton connections there, right? I think so, yeah. Yeah. So they were hired to drill the hole, and they didn't exactly get along with the goals of the expedition, even though they were. This is great. Yeah, I want to read a whole book about this. So this is like the plot of Armageddon, right? Exactly. Yeah. You get the drilling guys to be the scientists, and everything works out great. Yeah. Only it didn't. No, and they didn't even hire drilling guys; they hired construction guys. Right. So it was sort of doomed from the beginning, and it was one of these flashy sort of headline things. In the 60s, the U.S. really liked to do those sorts of things. We could do anything, right? You go to the moon, you go to the Mariana Trench. So we're going to send a bunch of construction workers out on a ship to drill to the core. Yep. This is Mantle, the plot of a movie. Has there been a movie about this? There is a movie called The Core. I think that Sean was leading me here. And aliens are in that one. No, there might as well be. It's ridiculous in that, but it's one of those on the list of terrible great geology movies. Right. Right. I don't know whose brainchild it was, but the production value is really good, and there's some big name actors in it. Yeah. Hilary Swank's in it, and Stephen Tucci, and
which one has
Aaron Eckhart's chin is in it.
Aaron Eckhart's chin is the top billing.
Yeah. They actually drill to the core with Aaron Eckhart's chin. Yeah, it's the plot of the movie. It might have been inspired by the Project Mohole expedition, but the gist of it is they have to drill to the Earth's solid core because it's stopped spinning and it's thrown off
Right.
the
And they
Earth's
have to
magnetic field.
reset it.
Yeah,
So they got to reset it with
Earth.
nuclear bombs,
Yeah.
nuclear detonations in the core. It's totally legit. It is. I would vote it as the greatest, worst geology movie.
yeah, that's up there.
It's
Sure.
spectacular.
Yeah, they have to drill 5,000 miles
Yeah.
in a couple of days. It's so
That's
dumb.
insane. Well, okay. So tell me about the science of how they drill. Like, of course, in the movies, you're just going down there. Yeah. All right. We got it. But the science, you'd think the water would kind of be used as an aid instead of a, deterrent, right? Obstacle that they have to get through of. So you would have to problem solve a little bit to use everything as help, right?
Yeah.
In order to get down there that far.
And this is where we might be able to have my buddy Jeremy Deans. He and his wife Allison Brink are supporters of the show, so they might actually
cool.
listen to this. So
All
shout
right,
out
yeah.
to them.
No, we'll put it up soon.
And maybe we'll try to get him on. But the article I read about an hour ago was talking about his role on the ship was different than previous expeditions. He was the geophysical guy on this expedition, meaning he was kind of driving or steering the drill. So my limited understanding as to how this works on a ship, a cruise like this, it sounds a lot like how a typical oil well or a water well is drilled, where you have a big bit that's sent down, and you just keep adding extensions to that as it goes deeper and deeper.
Right.
And then there's a special bit that retrieves core samples. So you have to send down mud to lubricate the thing. You have to deal with pressure and temperature. But a geophysicist can monitor the physical characteristics of the rock by using downhole geophysical tools. So the density, the porosity of the rock, if there's any fluids, gas, stuff like that.
Yeah.
So I saw photos of their lab on the ship, and it's sophisticated. There's a big monitor showing real-time geophysical logs. So it's just up to a geologist to sort of drive that.
Right. Right.
And he apparently did a pretty damn good job because they got to the
Yeah. And man, this guy's your friend, and he's not on our show right now. What the hell, man? We got to get him on.
Yeah, I was tempted to just try and call him like 30 minutes ago and say, "Hey, are you busy right
Come
now?
on, bro. Yeah.
Drop everything. Let's talk.
You need to be on the nights."
Well, this can be part one, and we can have part two.
I think
next
we
time,
can do a
think.
part two because I want to learn about what you just asked, the process, the logistics behind it, because that's what I don't know about. I know the importance of the mantle and studying the rocks, but the actual operations is what I'm really curious about.
Well, that's the beauty of science.
Sounds like
right?
it could be nail biting. It could be nail biting. They're monitoring shut it down. There's gas.
Yeah.
I'll bet it was cool. Like that.
Well, I'm sure they probably used some kind of sensor before they, so they weren't drilling right into suicide, right? Right into something that
it's
could
hard,
explode.
I don't know if they did seismic logging or anything like that. Seismic can't go down that deep. So it's a lot of, when you're dealing with geophysics, you're dealing with a lot of sort of remote sensing things. And seismic's the main source of of data that we use for that sort of stuff.
Yeah.
So the way the seismic waves, sound waves, bounce off of surfaces, how they pass through materials at different velocities. I don't know the technical part of that, but there's some magical mathematics that go on, computing that goes on that turns that into actual sort of remote imaging of the crust or the mantle or whatever.
Thomas, you just said something really interesting. You said that seismic doesn't go that deep. And I was under the foolish impression that this is how we know any of this stuff. Like, how else would we know?
Well, I
pictured okay.
Like seismic logs that are used in oil and gas industry, like precise seismic logs to identify discrete surfaces. We can
I
get
gotcha.
seismic tomography all the way down to the core mantle boundary.
Right. And is that not the way that we first kind of discovered the mantle and the core?
Yeah.
Could you maybe give us some of the background about how we even know the mantle exists, and that might set the stage for this discovery a little better.
Okay.
Yeah.
So hopefully everyone learned this in like elementary school, but we've got 3 layers to the Earth. We've got the core, the mantle, and the crust. The crust is really thin. The mantle is the most voluminous, the most massive part of the Earth. And then the core has a liquid outer core and a solid inner core. And it's dense iron, basically, iron and nickel. And it's seismic data. It goes back, several decades that we've known this, that has given us information about the deep parts of the Earth because we have, an array of seismograph stations on Earth's surface that are constantly picking up seismic data, earthquakes, right? Now, if you have a big enough earthquake that takes place on Earth, it can transmit enough seismic energy to pass all the way through the interior of the Earth and be picked up on the other side. Now, not to dive into the physics too much, but the 2 types of seismic waves that pass through the Earth are called body waves, are S and P waves. P waves are faster. They pass through both solid and liquid material. S waves are slower and will not pass through liquids. Okay, they travel at different velocities. They both reflect, meaning they'll bounce off of surfaces, and they both refract, meaning that they'll change their velocity and direction when they enter material that is of different density. So people who are smarter than I am, people who study geophysics, they can take those data that are collected from seismic stations on the surface of the Earth, and they can relate that to actual bodies of material within the deep parts of the Earth. So the earliest sort of picture we had was that we have, of course, our solid crust that we can study directly for the most part, but that our mantle is mostly solid as well, which is kind of mind-blowing if you think about it, because temperature and pressure is so great at those depths that you would expect things to be molten. Mm-hmm. And then we have our weird molten outer core and this solid inner core. And the reason we know that, and the reason we know the dimensions of the mantle and the core, is because those P waves will pass straight through the core because they'll pass through solid and liquid. Some of those P waves are refracted, so they change their direction, and they where they're picked up on the surface, it generates a regular sort of shadow zone, is what we call it, at the same latitudes on both sides opposite of the earthquake that generated those seismic waves. So by measuring the width of that shadow zone, or those shadow zones, you can do the trig, and you can measure the dimensions of the mantle and the core and all of that. The S-wave shadow zone goes from one latitude opposite to the same latitude on the other side of the globe, with no S-waves passing all the way through.
How long would it take for it to get from one side of the Earth to the other?
It depends on what it's traveling through. It's going to be different for each individual wave. So
Right.
It's usually depicted as kind of a like a vector, like a linear pattern.
Yeah.
But these seismic waves are traveling in all directions away from the focus of the earthquake, and they're also transmitting away from individual waves.
Right, I got you.
So when you look at the complexity,
Something in the ballpark of like the speed of sound, right? Or a little slower, maybe.
yeah.
I'm just spitballing.
Okay. Yeah, no, that's
Yeah.
good. Yeah.
But see, each one of these stations will pick up those seismic waves at different times. And physicists know the travel times of those seismic waves, and they can estimate the material they're passing through, basically.
Right.
And that's the extent of my knowledge on that. I'm not a geophysicist. But with modern technology, I think in the 80s, seismic tomographic imaging was developed. We can actually see individual discrete bodies within the mantle.
Yeah.
Like mantle plumes
Right.
of hot mantle rock that are rising up. We can see the convection of heat, which was theorized back at the turn of the century, that heat was convecting within the mantle, causing the tectonic plates, or at that time they thought it was just the continents moving.
Yeah.
And so we have this picture, we have this idea of what's going on within the mantle, and with that, we also know the change in thickness in the crust, basically the depth of the mantle. And that's where the term moho of the Mohole expedition comes in. That boundary between the crust and the mantle is called the Moho-Ravgic discontinuity. Moho for short.
Moho.
Yeah.
Oh, moho.
What does the long word even mean?
Moho-Ravgic. It's
Moho-Ravgic.
Yeah, the name of a Dutch scientist, I think.
Oh, it's a. I got you.
Yeah, I can't
Somebody's
remember.
name.
But we call it the Moho.
Good thing they shortened it.
So that's the target depth. If you want to drill into the mantle, you got to get to the Moho-Ravgic discontinuity.
Interesting.
And we know that depth changes dramatically between the oceanic crust and the continental crust, like Sean was saying. The oceanic crust, I think at its thinnest is like 6 or 7 miles. Miles, yeah.
Wow.
The continental crust is like 30 or 40 miles thick, if not more.
So that's what they were up against. Now, and then just off the top of your head, ballpark estimate, how far can like a normal drill, some of these drilling operations that want to go pretty deep, how far can they go? So the like diamond mine drilling and that kind of thing.
So the deepest hole that's been drilled is in Russia. It's called the Kola Super Deep Borehole, and that was drilled during Soviet times, and it still stands as the deepest hole, and it's around 40,000 feet deep, less than a third of the way through the crust.
Wow.
But like your typical oil well, we're talking a couple thousand at most.
And usually that's what deep drilling would be for oil, natural gas, gold and diamonds. Is that often like test wells for that kind of thing?
I don't know about test wells, but that's all done through mining. And I'm trying to remember the depth of the deepest mine. I think is still the Mopang mine in South Africa.
Right.
And I can't remember its depth. It's not anywhere near 40,000, but
no. Well, what were the Soviets up to when they were drilling 40,000 feet?
They were trying to get
their muscles.
Yeah, exactly. They were doing their good old Soviet muscle flexing, trying to get as deep as they possibly could. They got pretty damn deep. 40,000 feet is way down there, especially for I can't remember what year they were doing it, but
we are kind of hinting at some of the practical applications here, because the mantle has different stuff than the crust, right? Yeah. Some of these deep minerals, they're valuable. So if you can get, it's funny, I didn't do very much research for this show, never do, but when I Googled, I just wanted to see like the news article about drilling to the mantle, and what I got instead was some stuff about deep core drilling, and it was all stock options. And I wondered if those two things were related. I couldn't figure out if it was like a company that was involved in the drilling was shooting off because of the news, because of stock options were just going through the roof. And it had to do with, I don't know, like you said, to get to large amounts of gold and rare earth minerals and diamonds and things, you'll have to eventually go down and mine for it. Yeah. You're not going to get valuable amounts of that stuff from a drill bit hole. But I think for testing, they do some deep stuff, and that's what it was interesting that news article was happening at the same time as this news about getting to the mantle.
Yeah.
And so, really interesting.
Yeah. In ocean sediments and ocean rocks, there's, economic phosphate. So that might be what it was talking about. The gold and silver precious metal mines on the continent, they're getting that stuff secondarily from sedimentary rocks. So the source rocks, like granites and things, they have little flecks of gold in them. Sometimes microscopic gold, but when you dissolve them, you put that stuff into solution and it reprecipitates in the cracks and the partings in limestones and stuff, sandstones, sedimentary rocks. So like the Shafter silver mine, they're digging shallow mine shafts into sedimentary rocks. But yeah, I don't think this expedition had any sort of corporate contribution, because one of the things that's sort of frustrating the scientists whenever you read articles about this, the expedition is called the JOIDES expedition, and it's funded by NSF, and NSF is probably going to cut funding for it. So they've just made this spectacular find. They've reached the Mantle, and they're probably going to get their funding cut. So maybe there are some private interests who are considering funding the work. I didn't read anything about that. But.
It could have been a total coincidence that there was something going off on the corporate end and stock option version, but it seemed to be related. It's interesting. Do you know the backstory of why their funding is getting cut even after all this publicity?
There weren't a lot of details about it, but I would assume that it has to do with budgeting, federal budget stuff.
They're trying to keep us away from, all the things that live down under.
Yeah. Yeah. That's what the Ruskies were doing. They were trying to get down to hell.
Yeah. They're trying to get down to see their great grandparents.
Well, we didn't play the video. We queued up this video here. So the Kola super deep borehole that I mentioned before, the deepest, continental crust well, they dropped a microphone down the thing, and it sounds like what you would expect hell to sound like. It's pretty terrifying. So
we're gonna listen to it a little bit. So before we listen to it, all right, how many miles down did they drill again? Like, remind everyone.
This is 40,000 feet. So
it's like 20 miles, is it?
Yeah,
5,000.
So when you look from the Earth up into the sky, right before you get into the first layer of the atmosphere, that's like 5 to 9 miles. So you're talking 20 miles.
Yeah.
This is very, very deep, like deeper than when, the spaceship starts getting.
Does anyone know off the top of their head what the Mariana Trench, how deep that is?
Oh, the Mariana Trench?
Deeper than Everest is tall.
Yeah.
Oh, yeah, that's right.
Yeah, look up Challenger Deep. I can't remember.
Yeah.
I'm terrible with numbers.
Yeah, I'm too. All these are wild guesses, people. We're always shooting from our hips here. We never have anything in front of us. Never, and only occasionally do we ever check our facts, and we're doing it right
just
now.
Making it up. Okay, Conley's got it here.
35,876 feet.
Yeah, so deeper than the Marianas Trench.
Wow,
they
man.
If they dug it at the Mariana Trench, which would be really hard and maybe even impossible, they would have gotten to the Mantle there.
Potentially, yeah.
Good Lord. All right, well, we're going to listen.
Let's listen to hell, people.
To hell here. Let's see.
You might have to skip ahead a little bit.
Let's skip ahead after
It's been a while since I've...
Sounds like Santa Elena Canyon.
Voices.
Man. Okay. All right. Well, that sounds like every bar I've been to in Terlingua.
Yeah, it sounds like the Starlight on a Saturday night.
Yeah, exactly. It does.
Yeah, and it's too bad we don't have Honorbon here to explain it. But imagine it has something to do with like the reverberation of sounds at different pitches at that depth. But it's,
I mean, it sounds literally like hell. Like people are screaming, and I mean, you can make out certain voices.
yeah,
too.
it's bizarre. Yeah.
That is unbelievable. Wow. So, and it's the sound that we had before was like on the way down there.
I think
right?
so. Yeah.
And then you get down to a certain depth, and then boom.
Yeah. I
It's
can't
just
remember
like-
how deep they went with the microphone, but yeah, I mean, imagine you have a tiny shaft that's thousands of feet long, and there's sounds bouncing off of every single surface.
But this has been out for a while, right?
Yeah.
This audio track.
Yeah, yeah.
I remember hearing that and reading a little bit about it. But it's amazing to me. And I'm wondering now what the Mantle sounds like.
It sounds like this.
It does?
No, it doesn't sound like anything.
Oh, it's just quiet.
Yeah, it's very.
So
quiet.
are there like is it possible for there to be sections of the Earth underground that are hollow? Like you said, plumes were, and they would have to dry out, right?
Yeah, within the crust for sure, within the upper part of the crust. But things get weird when you get down to certain temperatures and pressures.
Okay.
And that's another reason the Mantle is so interesting, because it's solid, right? We know for the most part it's solid, aside from these these isolated bodies of molten rock down there, these plumes.
Sure.
But the most enigmatic part of the Mantle is between the uppermost mantle and the sort of middle part of the mantle. There's a layer that there's no way we're getting to. It's really deep, called the asthenosphere,
Yeah.
which is this bizarre layer that varies in thickness. But the rocks in the asthenosphere behave like more like a fluid. They behave like a ductile solid. They change their shape and their volume, and they don't return to their original shape, which is not how rocks behave at the surface. And that's what we think the tectonic plates kind of slide on top of that stuff. But the basic composition of the Mantle itself is all what's called peridotite. There are some differences in mineralogy as you go deeper and deeper, but peridotite is an ultramafic rock. So we think of rocks on the surface of the Earth or rocks in the crust. The most dense iron-bearing rocks, the rocks that make up the oceanic crust, are mafic in composition. So these dense black rocks. If you've ever been to Hawaii, basalt is a mafic rock, the rock that makes up the Hawaiian Islands.
Yeah.
And so the ocean floor is made up of that same stuff. And as you go deeper and deeper within the Earth, the material gets denser because pressure is increasing, and also because it's being drawn into the interior of the Earth. And that's why we have an iron-nickel core.
Yeah. Well, do you think, honestly, and this is a weird question, I have been wanting to do a show about this, but it kind of relates. Whenever you're in space, like astronauts, right? Like they age a lot slower than here on Earth, right? So if you had two twins, they did some kind of thought experiment, like in NASA or whatever. And if you have two twins and one goes up into space and lives, and the other one stays here, well, when the one comes down, it's going to be a lot younger than the one that stayed here, right? So time does shift. So when you go down, like, does a gravitational pull, could that shift time? Do you think that time can be manipulated in some ways down there?
Yeah, I don't know about that.
I mean, I'm
we
just
need honor
thinking,
bond
like,
for those kind of
it's just a
questions.
thought. It's
But
kind
if you sent a twin down to the Mantle, they would quickly
evaporate.
implode.
Yeah.
Yeah. Just to give you an idea of the extreme pressures at depth. So as you go within the Earth, there's a geothermal gradient where the temperature increases first at a regular rate and then it sharply drops off. But there's also a pressure gradient. And that gradient is an increase of 1 kilobar per 1,000 feet with depth. Okay. 1 kilobar is 1,000 times, and I might be getting these numbers wrong. I think I've got them right though. 1,000 times the ambient pressure at sea level.
Oh, okay.
So the pressure at sea level, multiply that by 1,000 with 1,000 feet of depth. So very quickly, at very relatively shallow depths within even the crust, the pressure is just incredible. And that's why rocks do weird stuff. Their melting point increases, so they don't tend to melt as readily.
Gotcha.
Yeah, they behave in more of a ductile fashion. So just the sort of physical, mechanical properties of the mantle are weird.
Yeah.
And not that drilling a core from the mantle tells us a lot about that, but it kind of is a starting point for better understanding that. At the very least, what excited me is I've been teaching that the mantle's made up of peridotite for years and years. And we have actual, what we thought were, and they really are pieces of the mantle, solid pieces of the mantle that came up through volcanic vents.
Right.
We call them mantle xenoliths. And they're made up of peridotite. So,
And
Hold on,
peridotite's
that's
a
cool. So
composition
where
of
do we
what?
find those? Where do we find those projected mantle pieces? And can I see one in a museum?
you can. We have them at Sol Ross. They're pretty common. Kilburn Hole,
Cool.
north of El Paso, has mantle xenoliths. I think I've seen them in Big Bend, although I haven't had a igneous petrologist confirm it. But yeah, if you have a magma chamber that's bringing up,
Don't they just look like, what do they physically look like?
peridotite is really distinctive. It's green.
Yeah.
The more iron,
Metallic green?
it's not metallic. It's
No.
it's transparent, translucent.
Translucent
It's really
green.
it's a beautiful rock. Yeah, it's green
Wow.
with little black specks in it.
Cool.
The
All right.
minerals, the main mineral is olivine, at least with
my
shallow
gosh.
peridotite.
And that's the blood of the earth.
It's like the body of the earth, really.
The body of the
Yeah,
earth.
yeah. The mantle makes up, like, again, get my numbers right. 67% of the volume of Earth, 80-something% of the mass. Yeah, it's
It's
most
a living thing, man. That's so cool.
well, compared to the other mechanical layers of the Earth, there's weird stuff going on down there. There's mantle convection. There's foundered pieces of crust that are floating around in there. There's
a little bit of
plume.
consciousness down there.
There's no consciousness.
There's got to be. I believe it. I believe
Just
there's
stop
consciousness down there. Yeah.
There's
Gotta be.
mole people. No. But one of the cool things about holding a piece of mantle rock, this is something that a geologist would geek out about, is if you think about when the Earth first formed 4.5 billion years ago, these are some of the first solid materials that would have formed as Earth was cooling. So not to get too deep into mineralogy or things like that. Minerals that have more iron and magnesium in them tend to be more stable at higher temperatures. So they're the first ones that will crystallize, solidify in a magma or a lava. So if you have the earliest form of Earth, where it's this big molten blob that's slowly cooling over the course of 100 million years, the first stuff that's gonna come together and solidify is that dense metal that forms the center of the Earth. So Earth is cooling, iron and nickel is crystallizing. It's going to the center of the Earth, right, forming our early core. And then what's left over crystallizes to form what's now our mantle.
Wow.
Olivine and these iron-bearing minerals, forming the most voluminous part of the Earth, the biggest layer of the Earth. And so the second stage of that is you have your early core, you have your early mantle, and then you have a magma ocean sitting on top of that.
Oh my gosh.
And that magma ocean starts to cool, and the next thing that forms is what makes up our oceanic crust,
Right.
basalt. So
Basalt,
it follows
exactly.
an order. And our earliest continents would have just been these tiny little bodies of solid mafic rock of
Just hard,
basalt.
just hard black.
Yeah, not super thick, really small in terms of their dimensions. And you take that, and then they start interacting with each other. They start colliding, subducting, partially melting within the mantle, and then you start getting more silicic rocks like what make up our continents. Our continents are essentially growing from that.
Yeah, and then a giant moon hits Earth and puts water on it, and then it has some kind of alien biome in it, and then we grow, and here we
Well,
are.
I'm glad you brought that up. So since we're talking about the importance of this, there's this sort of intrinsic importance to it, but you have to be able to justify the thousands, probably millions of dollars that were spent drilling this thing. It's not cheap to send a drill down to those depths. We're talking, bits that are hundreds of thousands of dollars. So not cheap. So you have to justify it. And one of the goals of the expedition and similar ones is to try and better understand the importance of these mid-ocean ridges, the mantle, when it comes to the earliest life on Earth.
Right. Yeah.
And one of the cool discoveries was there was always this idea that this process, it's an alteration process called serpentinization. So serpentinite is a metamorphic rock that forms from the alteration of ultramafic and mafic rocks. Okay. Mm-hmm. So we knew this was going on in the oceanic crust, the deep oceanic crust, and in the mantle. One of the byproducts of that, or two of the byproducts, are hydrogen and methane. Okay, so when serpentinite forms, it gives off a certain amount of hydrogen and methane. Like the black smokers in the deep ocean, these vents belch out hydrogen and methane. So we have a source for chemicals that could potentially be a source for life, right?
Oh, gotcha.
There are microbes that can take hydrogen and methane and synthesize it, right?
Yeah, just like the black smokers you mentioned are these crazy ecosystems.
Yeah,
filled
and, not,
with
and not a
critters.
poker group.
No.
And
okay.
they're the only ecosystems on Earth that aren't reliant on photosynthesis.
Interesting. Wow.
The foundation of those ecosystems is not photosynthesis. They're too far deep.
Yeah.
And so presumably if you have that kind of cool chemical reaction going on with serpentinization, like you mentioned, you could have little microbes growing on that stuff. And people have conjectured whether that might have been the origin of life. May not have been, in sunny seas with beautiful warm oceans.
Mm-hmm.
It might have been in a situation like that, much more mundane, much more hellish.
Yeah.
Well, it only has like how many billion or like millions of years to
the earliest
evolve.
evidence we have is 3.7 billion. So
3.7
yeah,
billion.
yeah. Prokaryotes
That's
have been
very
around for a
interesting
long
though,
time.
because what you described, this cooling of the asthenosphere, the cooling of the outer mantle, where it's in contact maybe with the very first layers of water, that could have been the first habitat available for life.
Yeah.
And
So
it would have been huge. It would have been enormous, right? Compared to what people have imagined, little localized black smokers. No, this is the very first contact of water with a potential habitat for life, an enormous ocean in contact with the mantle. That's brilliant.
yep.
That
Yeah,
actually
it
makes
kinda
a
works
lot of
perfectly.
sense.
Yeah.
You get life evolving pretty early, and then when real habitats start to become available with light and other fun stuff, then it just takes off.
Yeah.
But at first, it would have just been in this hellish environment of rocks kind of metamorphosing. I love it. I love it. That's
Yeah.
real.
Yeah,
that's
it would have
brilliant.
been. It would have been. So as this as minerals are crystallizing, they're giving off water too, and you also have comets that are striking the Earth, probably contributing water from the oceans.
Yeah.
Shortly thereafter,
That's
you have
brilliant.
heat that's vaporizing a lot of that, forming early atmosphere. So it all comes together pretty perfectly, and 3.74 billion years lines up with where we'd expect it to be, sort of the most extreme habitable conditions.
Yeah. Perfect.
And there's no
one thing that we often find that in really extreme environments, like the first kind of life form that became available to occupy that habitat sticks around for a long time. But some of the first land plants, the most primitive land plants, are still around, and they live in kind of extreme environments. Stromatolites are a good example. They're some of the earliest life forms. They've been practically unchanged for 3 billion years, and they're still around in hypersaline lagoons. So if they are drilling down to that mantle layer that has basically the same habitat, they could find early representatives of this first life form. They could still be around.
Yeah. Well, they confirmed that there's the right type of serpentinite down there for generating hydrogen and methane.
There you go.
Okay, so another big sort of foundational discovery.
Wow. So
Certainly worth
there
going
is a
back to see if
designer.
there's any bugs growing on it.
Yeah, that would be
Yeah,
that'd be really
cool.
interesting.
Yeah.
Yeah, and they didn't have to dig that deep. It's super thin there, so I think they went down 1,300 meters.
Into the mantle?
Yeah.
Wow.
No. In through the crust.
Oh, through the crust.
Yeah, it's just super thin there, right at the spreading center at the mid-ocean ridge. So they were able to punch through right there and get to the mantle. But I should mention that just like anything in science, there are people who are skeptical as to whether or not this is actually mantle rock from the main body of the mantle that they're retrieving.
Right. So Conley, let's test you here. What's the alternative explanation? What's the alternative hypothesis? What would the doubters be saying? And this is a good little mental game for our listeners to try. So we've
would
been
the doubters
convincing
be saying
everybody
that
this
the
whole
mantle
time,
rock
we made it
is?
to the mantle, but it's possible we didn't. So there's enough clues in what we've already talked about for somebody to come out with an alternative explanation for what they've discovered.
Oh gosh, the government, I guess. I don't
No,
know.
it's
Government
not.
cover-ups, like that's what
it's
what
always
I hear
more
all the
mundane.
skeptics saying, man. Like, but I'm
It's
not
always more mundane than it's not a conspiracy. So
not
Thomas mentioned, I forget the terminology he used, but he mentioned you can find mantle rocks on the surface laying around in the desert.
Right.
So it could have been ejected out of a volcano.
Yeah.
And you called them something like a
Xenolith.
xenolith.
Yeah. So it
So
could
this
be like a big chunk of foundered mantle that's
gotcha.
been brought up into these weird metamorphic rocks.
And
at the
we're
base.
just going into just a.
I mean, it's almost just as good
yeah.
if it were a big disconnected chunk of the mantle that got ripped out and is closer to the surface than it should be.
And there could be
That's
more
almost just
crust
as good.
underneath it.
It's almost just as good, but not quite, because it could have at the surface level, it could have been altered chemically, and it may not be the 100% pure mantle that you want.
But now that we have a hole there, doesn't that open up more possibilities for research and discovery?
Well, yeah, they
If
just got to
funding
kind of
continues,
confirm it.
Yeah.
Yeah, that's from what I understand, that's what a lot of these cruises have done is they have a research season, just like any other science. And then they abandon the hole, but then they come back and start drilling again.
Yeah.
And I think this borehole that they're drilling off the Azores, where they got down to the mantle, I think it's been drilled a couple of times before.
Okay.
So yeah, it needs the funding, and we'll see what NSF decides to do.
Yeah, we definitely got to get your friend on here and talk about the whole process of achieving this. I mean, it's a huge leap. It's a huge leap.
Mm-hmm. Yeah, and I was teaching during the first half of the summer, basically a physical geology class. It was for high school students, and I was looking at the news on my phone that morning and saw that they got to the mantle, and I ran into class because we had just been talking about plate tectonics, and it was like that scene from Dumb and Dumber. Where,
Oh, really?
Yeah, where Floyd sees the moon landing.
Oh, yeah. And
headline
he's like, we
in
landed
bar.
on the moon. Yeah.
We made it to the mantle. And of course, these lame 17-year-olds are like staring at their phones.
They don't even care.
It's like, you don't understand. They brought up core samples with serpentinite and peridotite.
And then they were just like, is this going to be on the test?
No, they just stared at their phone.
Oh, they didn't? Okay. All right.
They were on there with the news page that I found, looking at stock options and telling their investor to make the right decisions.
Probably watching some TikTok or something.
Yeah. Those adult cartoons that they all watch.
One last question, maybe. that I would like to put your way, Thomas, to maybe round out this, maybe ended on kind of a boring note. I've always been interested in metamorphic rocks, and how they, if anybody who's taken a 6th grade physical geology class or whatever knows about the rock cycle and 3 main kinds of rocks, igneous from magma, and sedimentary from precipitating out and forming, sand turns to sandstone. Metamorphic rocks are kind of the most mysterious. It's when any of those other kind of rocks get changed from heat and pressure and their minerals all change because of that heat and pressure. Would that only occur at the kinds of heat and pressure that you experience in the mantle? So does that mean if you find metamorphic rock, it has been sucked down that low, or has been pushed down, subducted down, or can you get those kind of pressures from ordinary tectonic processes, or is it some combination explanation of the two?
It only takes place in the crust.
Metamorphism.
Yeah, metamorphism takes place in the crust, because when you get to a certain depth, just everything except for those ultramafic minerals melt.
Right.
So it's either at a certain depth at like 800 degrees, whatever depth that is, depending on the geothermal gradient. Then you reach that sort of temperature threshold where you're mixing igneous processes with metamorphic processes. So there's a transition zone basically where you go from purely metamorphic rocks that you learn in your textbook,
right,
schists and phyllites and all that good stuff. And then there's a transition zone where you form migmatites. Migmatites are the highest grade metamorphic rocks mixed with magma.
And that's really cool looking stuff. Like a big rock outcrop of migmatite is just beautiful.
Yeah, it's like
you get all these bands and they're shot through with like quartz and stuff, and you can almost imagine they would have been semi melted because you get these wave like bands. They're incredible.
Mm-hmm. Yeah. So
here's where I'm getting confused though, because that all sounded 100% familiar to me. In fact, I've written about that before. But then if the mantle is not melted, I don't get it.
Well, it is melted in places. It's mostly solid. Right. But when you have, there's a couple of ways that you get melting within the mantle. You have to have what's called decompression melting, where you have one of these hot bodies of rock that works its way up through the mantle so rapidly that it carries its heat with it and reaches a temperature low enough for it to melt. Okay, so you can get melting like that, and you can get it by adding water. If you add water to hot mantle rock, it'll melt.
But then, so so what's the relationship between migmatite, which we just described, it's like metamorphic rock that's nearly melted so much so that a big outcrop of it appears to be wavy and like it's like Laffy Taffy or something. Yeah. What's the relationship between that and that other rock that you mentioned that the mantle's mostly made of?
Peridotite.
Peridotite.
Yeah. So is
that like one grade hotter and worse than migmatite then, where it's like semi-melted?
Yeah. When you get peridotite, to form peridotite, you have to take a rock that might be mafic and sweat out everything except for those iron-bearing minerals. So a peridotite is made up of olivine and pyroxene and some other minerals as you go deeper and deeper. And those minerals are really, really stable at high temperatures, more so than everything else. So everything else at those depths is unstable and it'll melt. Yeah. So if you take a slab of let's say oceanic crust and it dives down into the upper mantle, it's going to start to partially melt with depth. Yeah. And it's going to sweat out. If you have mafic rock, it's going to sweat out magma that has a lot of silica in it. It's going to have potassium, sodium, and those are going to reach a depth at which they're going to crystallize, or it's going to erupt as a volcano, and it's going to have quartz and feldspars and those types of minerals that make up the continental crust. So I think
I'm starting to get it.
Yeah, and the weird serpentinite stuff that they were looking at in these cores is coming from like towards the very base of the oceanic crust. Down there, you get a plutonic and intrusive mafic rock called a gabbro that's basically compositionally equivalent to basalt. But I should say that I'm sounding like I know a whole lot about metamorphic rocks, or that we as scientists know a lot about metamorphic rocks. Right. Admittedly, we don't, because out of all the three groups of rocks, they're the most mysterious, because not only do they form under incredible heat and pressure, and not all, you can form metamorphic rocks like around a magma chamber in the crust. It doesn't have to be at great depths, just most of them are. Yeah. But they're forming at such great temperature and pressure that we can't really replicate that. Igneous rocks we can study in real time because you can melt any mineral in a kiln. You stick it in an oven, you can melt all the minerals and see what they do when they heat up and when they cool off. But metamorphic processes are taking place thousands of feet beneath the surface at great pressure that we can't replicate. But also the component of time.
You can't date them either.
No.
You can't date them because they don't have fossils, because fossils get obliterated, and you can date the minerals inside of a metamorphic rock like you could a igneous rock or sedimentary rock, but you only get the time that they were crystallized.
Yeah, the stage of metamorphism.
The time of metamorphism, but not necessarily how long. So they're a mess. Well, I'm glad you said all that, because I always thought that was the case with metamorphic rocks, and I even wrote that somewhere, that like geologists quake in fear of metamorphic rocks. Yeah, and you're kind of confirming that, which I kind of made up off the top of my head. I figured that was the case. I quake in fear with metamorphic rocks. I don't know about geologists. They're really cool though. I grew up with metamorphic rocks. So I was unlucky enough to grow up in a place where metamorphic rocks were the bedrock, were common. And I wanted to find fossils, I was a kid, so I'm looking for fossils. And I'm in this huge band of really old metamorphic rocks, the Piedmont region of the eastern U.S., and I had no chance of finding fossils.
It sounds like you had a really schisty upbringing.
That's good. Hey, tell us where a local West Texas person can see a metamorphic rock.
If you drive west of Van Horn on I-10, the road cuts just as you get kind of in between Van Horn and Sierra Blanca, those are metamorphic rocks. Yeah. You can go, as you get closer to El Paso, you can get into some metamorphic rocks. Not accessible to the general public, but south of Van Horn, in the Van Horn Mountains, are high-grade metamorphic rocks exposed. So
exposed.
The only places you find them is where you've had significant uplift. You've had big mountains that have been pushed up and then eroded down to their core.
Right.
In North America, we have the Canadian Shield, which is basically the core of the continent exposed, where glaciers eroded down into the metamorphic zone.
Yeah, it's interesting that the continental shield of all the continents pretty much is made of this really old kind of core of metamorphic rocks. Mm-hmm. It's really interesting.
Yeah.
Huh.
Yeah, and
so there's none in Big Bend area?
There's low grade contact metamorphic rocks. Oh, okay. So the other way that metamorphism can happen is if rocks are in contact with a magma chamber.
Okay.
But it's really restricted. It's like 100 feet around the magma chamber.
Wow.
Okay. But nothing you would consider to be a moderately graded metamorphic rock. It's sedimentary rock that's been baked into
I got
terracotta.
It's not.
So it is a cool thing about the greater Trans-Pecos has such a great variety of stuff that there's a really good high grade metamorphic rocks, or medium. I don't know if they're high, but good metamorphic rocks near Van Horn. Plus you got all this great, sedimentary rocks with fossils, plus all the ancient volcanoes. So you got everything there. Mm-hmm. Not like poor lonely budding geologist Sean Graham sitting on top of
red
regional metamorphism near Atlanta. where you can't tell anything about the rocks by looking at them. It's like, what the hell is going on here? You have no idea how old they are, what they are.
Yeah, and
So,
I think
biology.
to wrap
Little
up with
plastic
metamorphic
shovel.
rocks. The temperature and pressure it's hard to replicate, but time is really the component that makes them so
Right.
confusing because even though we don't get the same sort of precise age dating like we would in an igneous rock, we can age date those individual minerals. With modern technology, we have these instruments called laser ablation instruments, where you can take an individual mineral crystal. They've done this with garnets in metamorphic rocks. You can take a little slice out of it, the cross section. Garnets, because they grow so slowly, all silicate minerals have a really slow reaction rate, so they grow slowly if they're allowed to.
Yeah.
These garnets have little growth rings like a tree, and you can take this laser ablation tool and zap each one of those layers, and you get the isotopes from that and run it through a mass spectrometer, and you get age date for each one of those. And they've been able to calculate or estimate the growth rate of these things. And again, I'm going to try to remember the numbers. It's 1 millimeter of growth per million years.
My gosh.
Okay, so a millimeter
Wow.
is like half of a pencil lead
Yeah.
per 1 million years. I've seen garnets that are 1.5 inches in diameter.
Whoa.
Yeah.
So take that and extrapolate that out. We're talking millions and millions and millions of years worth of time.
Garnets the garnets are so underrated, man. You could have a garnet ring for $20 or something like that. It's like a semi-precious stone or something. They're really beautiful. It's burgundy color.
Yeah.
If you find a gal who likes garnets, that's a keeper.
See, yeah,
But,
for sure. Yeah, absolutely.
That's a joke. I always tell
that
my
makes
class.
them that should be that should add to the value right there. They're like corals that grow over hundreds of thousands of years.
Yeah, but
Amazing.
it's red.
Yeah,
so-
it's like a burgundy color.
Yeah.
They're beautiful stones, and that's why I always joke with my class. I tell them, I said, if your significant other ever gives you a piece of garnet jewelry and you think that they're being cheap, it's like now they're giving you something that's millions and millions of years old. And you can treasure it.
And it's all real. Yeah.
Yeah, and I told them
Value.
if you give your significant other if you give your girlfriend or your wife or whoever a piece of garnet jewelry,
Yeah.
you can convince them that you're not a
Yeah.
and you can
And if you're ever
lecture them on.
if you're ever rock hounding and you find one of these metamorphic outcrops, look for garnets. They're often studying little nice metamorphic rocks, and they're not going to look bright and beautiful like on a diamond, like a ring or
But
something.
you have to tumble them.
But-
and
Yeah,
get
you
'em.
can polish them
you
into
polish them.
semi.
They are pretty nice, but you'll see little centimeter wide garnets sticking out of those things, and then with that in mind, how long that would have taken to
Wow.
cool slowly. Amazing.
Yep.
I'm going to go looking for garnets.
Yeah, you can. They're in the Van Horn Mountains.
Okay.
I don't know if any of the exposures. Those are all mostly amphibolites that are exposed on I-10, and you don't want to pull over on that stretch of I-10 anyway.
No, it's dangerous.
I know where there are garnets in the Van Horn Mountains.
Really?
Yeah.
All right.
I've got a sack full.
Time for an expedition.
Yeah.
Time for an expedition. No, man, that's great. That's great. I've always been told to stay leery from women who wear red rings. It's the blood they suck out of the souls of their past mates.
Or they could be geologists who really appreciate the time that it takes to form a garnet.
I guess that's possible too.
Although there is some
He doesn't want anything but a superficial explanation. So yes,
Exactly.
Conley,
Yes.
they're vampires.
They're vampires.
Exactly. See, Sean gets me.
Yeah.
You understand. See, they could be. I'm just saying. Man.
Yeah, it's some experiences.
Possible. But anyway, all right. Well, there you go. This is part 1, hopefully of part 2.
Yeah, let's try to get Deans on the show.
Yeah, we'll try to do that.
Only if he's a good storyteller. If this guy bores me to tears, And he's like, the food was pretty good on the ship, but after I got to read a few books and I caught up on my Russian literature. So I want you to vet this guy because I don't want anything but nail biting stories about pressures almost blowing up the ship and the time they were retching their guts out because the thing was lolling in the ocean.
And pirates.
Check him out. Check him out.
I think
if you can tell a couple of good stories, I want him.
Okay, yeah. Well, we're throwing down the gauntlet, Jeremy.
There were sharks all around.
Yeah, come up with some good stories.
So
Dr.
there
Beans.
I was. All right. Well, another episode of Science Nights in the books.
Yep.
We'll see you next week. Take care. Thanks for listening to this episode of Science Nights in the Morning. Be sure and follow us on Patreon for exclusive gear and uncut episodes. Check out the latest science articles on our Facebook page and subscribe to us on YouTube and your favorite podcast listening app. And if you got a question, we'll join the discussion. Hit the hotline at 432-217-1983 and record your message. We couldn't do this without you, and thank you so much for listening each and every week. That's Science Nights in the Morning with a K. And we'll see you next time.